fire out. Buenas tardes, bienvenidos al Planetario. Welcome to the Planetarium. This is a special opportunity. Es una muy buena oportunidad para todos nosotros to have here those special guests because they are one of the most important people in NASA, JPL. I mean, being in JPL as well, and celebrating the 60th anniversary of the Robledo Station, de Chavela Station. Es una oportunidad, han venido con motivo del 60 aniversario de la estación de Robledo de Chavela, que como sabéis es una de las estaciones de espacio profundo de NASA. No quiero hablar mucho porque son tres intervinientes. I'm not going to speak very much because there are three speakers, and I will let the voice to our guests as well. And give me the microphone, because we also have here, push the slide please, another guest who is going to introduce our speakers. Le voy a pasar el micrófono a Tonya McNair, who is a Deputy Associate Administrator for Management Operations, Space Operations. She's going to talk about all our special guests and speakers. Ella va a hablarnos de los tres principales actores de este evento, que para nosotros es un honor tenerlos aquí. NASA es una institución que colabora no solo con el espacio, sino también con nuestro planetario, a una escala, por supuesto, más modesta, en nuestro caso, quiero decir, pero estamos muy agradecidos. Marcus Watkins y mi paisana Lola Cadierno. Marcus Watkins es el director de España y Portugal de NASA, y Lola es, pues, casi mi hermana. Bueno, please, thank you very much. Gracias, Tonya. Please, your turn.
Good evening, everyone, and welcome. We're very excited to be here. We're in country this week to celebrate 60 years of collaboration and partnership with Spain, with the Madrid Deep Space Communications Complex. And we're excited for the next 60 years for the work that we are going to embark upon with our Artemis programs and our scientific discovery programs. So you're going to hear from some great leaders about our enabling our future for scientific discovery and human exploration. You're going to hear from Miss Andrea Razzaghi. She's going to talk to you about some of our science discovery efforts. Charles Thornton will be talking to you about enabling technology, and Kevin Coggins will be talking to you about communications. So I'm going to hand it over to Andrea. Andrea, welcome. Thank you.
Is this on? It is. Buenas tardes. It's a pleasure to be here at the Planetarium and to be here for this very special occasion of marking 60 years of partnership and collaboration with the Spanish government for deep space communications. So I'm going to talk to you tonight about how NASA enables scientific discovery. Okay. All right, so I'll tell you a little bit about myself, talk about NASA, who we are, and then show you how we explore. So here I am about 20 years ago, standing in front of a very complex spacecraft. And I wonder, how did I get here? How did I get to a point where I could stand in front of this amazing machine and know everything about it, every nook and cranny, every wire, every problem we solve, and get it ready for launch? And I go back to when I was a little girl and we moved into a new house, and my sister was on the way, and we outgrown the house we were in. And we had this fixer-upper, and my dad, he collected a lot of power tools to do a lot of work. And I wanted to know how to use those power tools. And he showed me how to use them safely. And I thank him so much for not discouraging me. He never once said, girls don't play with power tools. And then I discovered math when I was in school, and I just really loved how solving math problems was like solving puzzles. And then fast forward, when I was thinking about going to college, I was talking to my college advisor and said, what do you like to do? What do you want to study? I said, well, I really like calculus and physics. And he says, well, you should think about being an engineer. I actually didn't know any engineers. And I'm like, okay, sure, that'll be great. I'll study engineering. And so that's how I started my progress. So what am I up to today? So this is what I see every day when I walk into my building, dare mighty things. And I am the government official at the Jet Propulsion Laboratory in Pasadena. And I would say, forget about that title you saw, because no matter whatever job I've ever had at NASA, I think of myself as doing one thing, and that's enabling scientific discovery. So, NASA, who are we? Our name is, and our brand is known around the world. And most people think, oh, NASA. And I ask people often, do you know what NASA stands for? And I'm surprised. A lot of people actually don't know. If you think you're confident, think about that. But we're the National Aeronautics and Space Administration. So if you look at the national administration part, that tells you we're part of the government. We're part of the US government. We're an independent agency. We're not a part of another department. And the first A in NASA is aeronautics. That's the part a lot of times people don't think about. But we enable technology development and innovation for our aviation industry, how you can fly cleaner and safer. And, so that's the first A in NASA. And then the S, that's space. That's what people typically think about when they think about NASA. And the first thing most people think about is astronauts in space. And that's obviously a very huge part of what we do. But the other part of space is where I've spent my career, and that is on the science side, where we keep all the human beings on Earth and we send our robots out to explore. So that's the part of NASA I want to introduce you to today. So one of the places we explore is our home planet, Earth. It's, obviously very important to all of us because we want to know, get as much information as we can about our home planet. Then another area of scientific exploration is in heliophysics. And this is one that a lot of people don't necessarily think about, but we live with a star. The sun is our star. And then there's this relationship between the sun and this amazing thing called the magnetosphere that protects Earth from what can be the harmful radiation that comes off the sun. And it's a very important part of our system here that keeps life on Earth safe. And there's also a phenomena called space weather. And so that's part of this scientific area as well, looking at that, what's going on in space and how it can affect our satellites and our power grids here on Earth. And then this is our neighborhood. We are part of this amazing solar system. So we want to get out of our, we want to get out and explore around the solar system and understand the place that we have when we all formed about 4.6 billion years ago. And then I call this our wonder. This is the area of astrophysics. And since the beginning of time, humans have looked into the night sky and wondered, what is our place in this universe? How did this nice night sky, come to be? And one of the biggest questions that humans have thought about since the beginning of time is, are we alone in the universe? So collectively, this is our exploration space. And this is what I want you to think of a number. So if you imagine the missions that NASA has going on right now in science, I want you to think about how many missions do you think we have going on right now? And what I mean by that are things that we are designing, missions we're designing, to missions that are in what we call extended life. So get a number in your head about that. Everyone think they have something? Yeah, this is it. These are all the missions that we currently have underway in science at NASA, about 140, and at any given time, we've got about 140 science missions underway. So I'm gonna just talk about a few of the ways we've explored in those science areas, and I'm gonna start with our home planet. Right now, we've got over 20 missions circling our home planet and helping us understand everything about what's happening with our oceans, what's happening with changes on land, deforestation, what's happening with our atmosphere. They often work synergistically with each other so we can get this amazing picture of what's happening with the health of our home planet. And with the vantage point of space, you can cover the entire planet if you're going around the poles in just 16 orbits and get a full picture. And think about that compared to what you would do if you're just observing on the Earth, and think about all the places that are hard to access, like the tops of high mountains or in the middle of the ocean. And we can easily view all of Earth from the vantage point of space. So I'm going to go back to the picture I showed earlier. And so this is an Earth science mission called AURA. And it looked at it's still looking at atmospheric chemistry. Because this launched 20 years ago, and it's still working. We designed it to last 5 years, but we always really overachieve when it comes to how well we build our satellites, so they can keep giving us valuable data long after their original intended lives. And this one looks at what's happening with the ozone layer, what's happening with air quality, and what's happening with our changing climate. And the picture on the right there is with me and my husband in front of the rocket, just to give you some scale. That spacecraft, and that's the spacecraft without its solar arrays on it, is about the size like a school bus, and it's sitting in the tip of that Delta II rocket there. So moving on to heliophysics, this is the Parker Solar Probe. It is the spacecraft that's gotten, we say it touches the sun. It actually flies through the atmosphere of the sun, and it's the closest observation we have had, of our sun. And just think about the technology development you go to build something here on Earth that has to survive the atmosphere of the sun. So some amazing technical challenges that the team had to overcome in order to build this spacecraft. So now I'm going to go and tell you about a few different missions in planetary science. Now, this is a mission that's near and dear to my heart. It's the last mission I actually worked on as a mechanical engineer. And this is an artist concept here, but what I'm going to show you are some real images taken by this mission, and it's like about 13-year observation of the Saturn system. And I like to say that if you were in your little spacecraft flying around the Saturn system and looking out the window, this is what you would see. You would see the majesty of the rings of Saturn. You would see the moons, which we now count at 146 moons. And one of the things that we've discovered about the moons is there's one called Titan, which is the only other world in our solar system that we know to have liquid on the surface. It's not liquid water, though. It's methane and ethane, seas of methane and ethane, and it rains methane and ethane. We have a little tiny moon called Enceladus, which is the brightest object in our solar system, and it's covered with this fine snow. And we think there's a possibility of actually having an ocean underneath it. That's one of those places where there could be the possibility of some life even today. And going back to Titan, when we look at that, we think that's what Earth may have looked like at some point in our history. So it gives us some clues to what Earth may have been like at one point. And I love this image. That little pale blue dot is where we are. So if you were in your spacecraft flying around Saturn, looking at the window, and you want to wave home, there you are. So how did the Cassini mission end? So I think I mentioned, we have this chance that there may be some of these moons that have the possibility of life, and we have this spacecraft built here on Earth. And the last thing we'd want to do is for it to crash into some world that could have the possibility of life and cause some contamination. So we decided we're going to fly it right into Saturn. And this is an artist's concept of what that would have looked like. And there should be sound for this.
Plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends as Cassini becomes part of the planet itself.
I still get a little emotional seeing that because I was there at the very early design phases of this mission. And then in one of my positions, it was one of the missions I was responsible for, and I was there when it sent its last signal. So what just happened on October 14th, less than 2 weeks ago? We launched a mission to the moon Europa. And this is a moon around Jupiter.
For NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff, the Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
And this is on a SpaceX Falcon Heavy launch vehicle.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight.
Now they wait for acquisition of signal.
And I believe we have it. Right. There it is. Confirmation of signal from the spacecraft Europa Clipper.
So 5.5 years from now, we will arrive at the moon Europa, and we will take a close-up look, a closer look than we've seen from some of our prior missions. So this gives you a little idea of how the spacecraft is going to come down and observe this very fascinating moon. Now, if you look at these images, this is from prior missions that we know what this moon looks like. It's covered in ice. And so one of the questions is, why do we care about this moon? So from our prior observations, we think this is what's going on there. There is this thick ice crust estimated to be like 10 to 15 miles deep. And then underneath that, there is evidence for a possible salty water global ocean. And it has mechanisms from internal heating. And we know from on Earth, when we go deep into the sea, we're far away from our sun, that we have found life. And so we're looking for that question. Is this a place that is habitable for life? It's a very compelling question, and we are going to get more information about that with this mission. Now, some of our other planetary missions, we've actually landed on other worlds. So how do you do that? And I'm going to take you back to 2012, when we landed the Curiosity rover using a new system, because it's the first time we were trying to land a 2-ton rover on the surface of Mars. So I'm going to show you and let you hear directly from the engineers who had to solve all the problems, all the challenges you would have at Mars, and how they did it, and how they figured all that out from Earth.
Look at it. It looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the skycrane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
I still get chills watching this, and I've seen it, I can't count how many times. And we did this again with the Perseverance rover, which is on the surface now, along with Curiosity, still exploring, but the Perseverance rover is picking up samples that we're later going to bring back to Earth and study here in our labs on Earth. Just think about the creative and innovative teams it takes to figure this all out. And I want you to imagine, you hear a lot of talk about humans going to Mars. They have to deal with all the same challenges. So imagine what it's going to take to solve those problems to get humans to the surface of Mars. So now I'm going to go to astrophysics and how we explore our great universe. And so we have the James Webb Space Telescope now exploring 1 million miles from Earth at a point called Lagrange Point 2, 4 times farther from Earth than our moon. And just to give you an idea of the size of this, this is a full-scale mock-up of this telescope, and that big sun shield you see there is like the size of a tennis court. So think about this. This is the telescope we need to take astrophysics to the next level. How did we get this on a rocket and get it launched into space 1 million miles away from Earth? We use spacecraft origami. So not only did we have to design this amazing telescope so it would be in that form that I just showed you in space, but we had to also design it so it could fold up into the nose cone of a rocket. So once it got to its observation point, it had to deploy and unfold into its final form. Another example of having to use a lot of creativity and innovation to solve some really challenging issues and problems in the pursuit of scientific exploration. So if you haven't looked, there are some amazing images. And so for a lot of people, the images are just gorgeous images unveiling the universe to us, but they are teeming with interesting scientific information for our astrophysicists to help us better understand our place in the universe and indeed rethink what we think we know about the universe. One important thing about science is you revise what you think you know based on new information. And I'm going to quote Dr. Ed Stone, he was the project scientist for the Voyager missions, which are still going 47 years after their launch. They're the farthest things from Earth that humans have ever created. And several years ago, we had a press event because it looked like one of the spacecraft has moved into interstellar space, so beyond the influence of our sun. And one of the journalists asked him, he says, "What are you discovering now that you're moving into interstellar space?" And his answer was, "We are proving ourselves wrong every day." And I love that answer because confirming what you think you know is one thing, but learning about things that you didn't even imagine is even more exciting in the world of science. So I'm just going to share with you a few of these magnificent images that James Webb Space Telescope has brought us. And I encourage you to go online and take a look, and I suspect you'll get lost there for a while because there's just so many beautiful images to explore. So how do we know things are going to work in space? Our atmosphere here is very different than where we explore. And also we've got, you've seen a video of a launch, we've got to get things through this very violent experience of a launch. So we take our delicate hardware and we simulate these environments here on Earth. So we shake them because if anything, that we thought about doesn't actually hold up, then we want to fix it here and not have a problem when we actually are taking it through the real event. So this is simulating the vibration that a spacecraft is going to experience during the launch event. And then we put them in these big thermal vacuum chambers to simulate the environment of a hard vacuum and all the extreme temperature changes, and way more extreme temperature changes than you would experience in your day-to-day life here where we live. So very important test to get through before we are ready to send our missions into space. And I've touched on this a few times, this question of are we alone? So one of the most exciting areas we look at is exoplanet, and our next colleague, Dr. Charles Norton, is going to tell you a little bit more about that. But we used to wonder if there were other planets around other stars. And because of our exploration, we know for sure, we have validated that thought that pretty much every star you see in the night sky has at least one planet and likely more. And we've also looked at what we call the habitable zone. So our planet, Earth, is what we call the habitable zone of our sun. That means it's far enough from our sun that we can have liquid water and not too far. And so it's just right. And so we're looking at that, at these other planets that we found, and even thinking about some of the moons, because we know in our own solar system we have moons that can have those attributes too. And so we know that these are abundant, in the universe. If you think about what we know about the universe, in our galaxy alone, the Milky Way, we have 100 billion stars. Think about 100 billion stars. And recent data from the Hubble Space Telescope has shown us that we have as many as 2 trillion galaxies. James Webb Space Telescope is probably going to reveal even more, and it's already revealed some very interesting things about early galaxies. So do that math. 100 billion stars times 2 trillion galaxies and tons of planets, many of them rocky and similar to Earth. So the question is, are we alone? And so we have some fun, some of the interesting planets that we have found. We've created these kind of retro-looking travel posters, like if you were to go to these places, how would you advertise them? And one of these, the dark one, where it says, where the nightlife never ends, we found what we call rogue planets, planets that are not orbiting a star. Like in our understanding about planetary formation, they have to be around a star. So what happened here? How did they get kicked off the team and, it's floating around in space by themselves? There are different types of stars. We have a particular type of star, but there's something called a red dwarf. So where the grass is always redder on the other side. Maybe if there's vegetation, it's different than what we have here on Earth. And then one of the most exciting, findings is called a TRAPPIST system. So we found a system where there are 7 rocky planets orbiting a star, and 3 of those seem to be in the habitable zone for that star. And if you were looking at your window, you can imagine looking at your window and seeing other big planets right there. And with our technology, if we had this, we could actually go planet hopping. Can you imagine that? So what might the future hold? So think about the exploration ahead of us, all the questions that we still have to answer, and especially what is one of these most compelling questions: are we alone? Are we going to find evidence that there is life someplace else in the universe? And with that, I'm actually going to turn the podium over to Dr. Charles Norton to tell us about some technology development.
Thank you very much, Andrea.
Is that how we're doing?
No, please. Dr. Thornton is going to talk about the technology and NASA JPL. Thank you very much.
Oh, thank you very much. That was a wonderful overview, Andrea. Thanks so much. Let's see if I can bring up. Okay, Hola todos. How is that? Hello, everyone. Welcome so much. It's my really great pleasure to be with all of you today to celebrate the 60th anniversary of the Madrid station and to share with you some of the technology-related activities that we're involved in at the Jet Propulsion Laboratory and within NASA. So as mentioned, I'm Charles Norton. I'm the Deputy Chief Technologist of NASA's Jet Propulsion Laboratory. And as you may know, the history of JPL actually dates back to the 1930s, when a professor at Caltech Theodore von Karman and some of his students were performing rocket experiments in the arroyos just above Pasadena, where JPL currently stands. And as a result of the work that they have done, it really led to the formation of NASA. Of course, in 1957, the Soviets won the initial space race by launching Sputnik. But not long after, in January of 1958, JPL launched Explorer 1, which was America's first satellite. And it was a satellite that helped discover the Van Allen radiation belts. And not long after that, NASA was formed, and JPL was brought into NASA as part of the organization. So at JPL, our main goal is to perform remote exploration of the solar system. And one area that we're looking at very closely, which Andrea talked about, is the search for life, and are we alone? So what I'd like to do today and this evening is to talk to you a little bit about the technologies that are involved in doing that and the scientific discoveries that we hope to make along the way. And there are 3 areas I'd like to focus on. As was mentioned, I want to talk a little bit about exoplanets, then lead into the possibility of discovering the chemical signatures of life on icy moons, and then touch on the work that we're doing with the Mars 2020 Perseverance rover. And JPL is really all in on trying to find mechanisms to help us understand whether or not there may be life or the chemical signatures of life within our solar system and beyond. So exoplanets are very easy to understand in some sense. They're simply planets that exist beyond our solar system. And much has been learned about these exoplanets just really within the last few years. We now know that every star has planets that orbit it. And if you think about it, with billions of stars in our own solar system, there are many billions of potential exoplanets that exist around those stars. But they're very, very hard to detect. You know, the stars are very bright, and it could be very difficult to observe these exoplanets. But there are mechanisms that we use. One is called the transit method, where as a planet actually passes in front of its host star, it actually dims that star, and that's a way we can detect these exoplanets. There's a method called the radial velocity method. Again, as these planets orbit their host stars, they can cause those stars to wiggle a little bit. And it turns out that through observations, those stars actually change color, and that's something we could measure, and it's a way that we could determine certain properties of exoplanets as well as their existence. As you can see here, we've discovered over 5,000 exoplanets thus far, and many of them are clustered in a region roughly 1,000 light years away from our own solar system. But in fact, the closest exoplanet, Proxima Centauri b, is only about 4 light years away from Earth, so you can almost reach out and touch it. It's really a next-door neighbor in intergalactic scales. But as I mentioned, there are some mechanisms where we use to discover these exoplanets. One way we really want to try to learn more about them is through direct imaging. And we're working on technologies that can enable that. One of them happens to be a coronagraph, which is an instrument that will fly as a technology demonstration with the Nancy Grace Roman telescope scheduled to launch in 2027. And most typical coronagraphs basically place a mask or a shield around the host star to block its light to allow you to discover those exoplanets around it. But this coronagraph that's been developed at JPL with our partners is very special because it's going to use a destructive interference technique, and it's a mechanism which will allow us to actually observe exoplanets 1 billion times dimmer than their host star. So why don't we take a quick look at how coronagraphs work. So this is the coronagraph that will fly on Nancy Grace Roman. If you look at the electronics and the technology, it consists of deformable mirrors, items called occulters, and together these allow you to make these measurements. It's a very complicated instrument, actually one of the most complicated instruments that JPL has ever delivered. Let's take a look at how they work.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
Yeah, it's quite incredible how these chronographs work. In fact, those deformable mirrors can adjust the imaging in such a way that we can increase the precision really down to levels as tight as the strand of a DNA. So it's really quite impressive. And as was mentioned, just last week, we launched Europa Clipper, and it's on its way to Europa, this icy moon of Jupiter, one of the so-called Galilean satellites. It's actually the largest spacecraft for planetary science that NASA has ever built and launched. And we're very excited about its mission because its goal is to help us understand whether or not Europa has the ingredients and the potential to support life. It's not a life detection mission, but it will tell us a lot about the potential. So this is Europa. What's special about it is that, of course, it has this icy shell and it has this subsurface ocean. In fact, Europa is about the size of Earth's moon. And Europa, in addition, has many of the ingredients that we look for in terms of life detection. There's water, there's an energy source, and the chemical constituents that we know exist there tell us that there is the possibility of having life possibly in that subsurface ocean. And Clipper is carrying many different types of instruments, 9 instruments in fact, so gravity instruments, spectrometers, visible imagers. It even has an ice-penetrating radar. And all these instruments together will help us understand the geological properties of this small moon. In particular, we're very interested in understanding what's happening at the ice-ocean boundary, as well as other properties. But in terms of the technology, in the long term, we really would like to get down to that subsurface ocean. So we have been exploring new robotic techniques to allow us to get there. So let's take a look at one mechanism that may occur.
Targeting the strongest jet, a spacecraft would land near the jet's source, a vent in the ice. Once on the surface, the Exobiology Extant Life Surveyor Robot, or EELS, would leave the lander and travel to the edge of the vent opening. After assessing its surroundings, EELS anchors itself to the surface to push against the force of the vapor coming from the jet. It then places its sensor head into the jet streamline. From this first-of-its-kind surface experiment, scientists will learn more about the mechanisms driving the jet activity and the chemical makeup of the spray. But to truly characterize the ocean that lies beneath, EELS must venture deeper. Guided by pressure sensors, EELS would autonomously follow the flow of vapor streaming up the vent. It pushes on the side walls of the vent conduit, where the ice, heated and pressurized by the vent flow, acts remarkably like ice here on Earth. EELS consists of many counter-rotating threads that act as self-propelling ice skates that grip and move the robot forward against the jet forces. By adopting a spiral configuration, EELS adapts to the vent's uneven interior. It reconfigures itself as it goes, based on the forces its sensors measure from pressing against the walls. Researchers think that, deeper down, the vents most likely constrict to a smaller diameter, forming a narrow throat. EELS is designed to adapt to this, becoming a self-driven screw, able to power through this point of greatest pressure and flow. Once in the water, EELS propels itself using its spiral threads and uses its instruments to see if it swims alone. And maybe one day, on a follow-up mission, this intrepid robot might venture even deeper to the hydrothermal vents on the moon's sea floor to search for possible alien nurseries of life.
Yeah, so a snake robot is a very, very different kind of instrument that we're used to building, but it offers great potential in addition to other techniques like melt probes, which may be able to melt their way through the ice down to that subsurface ocean. And of course, moving on from Europa, of course, we've been very, very interested in Mars for many years, have landed a number of rovers, made many observations from space, and have learned a lot about the properties of Mars. But of course, with the Perseverance rover, it's been very active, collecting geological samples of igneous rock and other types of rock, even the atmosphere, to help us characterize whether or not the chemical conditions existed for life to have existed at one time on the red planet. And it's a very sophisticated device, the sample caching system, which is collecting many of these rock samples, which will then be returned to Earth on a future Mars sample return mission. But as you can see, it's a very large rover. It's about the size of a Mini Cooper. So we did have to invent and adapt other technologies associated with getting this rover down there. So as you can see, this is where the rover is currently exploring in Jezero Crater. You can see the path of the rover if you follow that white line in the brownish area. And you can see how at one point this was an area where water would have flown into this particular region. And it turns out, though, that to land in this region, you require very precise mechanisms to get you where you need to be, because there are hazardous areas in Jezero Crater. So this is actual imagery that was taken during the landing of the Perseverance rover, the first time we were actually able to do that. So you were able to see the parachute deployment and the sky crane that you heard about earlier, which is lowering the rover into Jezero Crater. An important capability that was flown on this mission for the first time was terrain relative navigation. So as the rover was entering the atmosphere and imaging the ground, in order to ensure that it could land safely, it used a very sophisticated set of imagery and other remote sensing instruments to precisely guide it to a very specific pinpoint landing location. And as we continue to explore Mars, those types of technology capabilities will be essential for our ability to achieve the most science. And in fact, as many of you may know, we flew the Ingenuity Mars helicopter, which was the first time we flew an aerial vehicle on another planet. And you can see an image of it up on the top right there. But we want to try to advance this technology to help us make other discoveries at Mars in regions where rovers and orbital instruments cannot easily make observations. In fact, we've even been exploring the role that rovers could have to collect samples. And in the far distance back there, there's a future concept that we're working on called the Mars Science Helicopter. And I'd like to show you a little bit about the capabilities that such a science helicopter could enable. So as you can see, this is a helicopter that has 6 rotors on it, and it will have the ability to fly into these tight regions where rovers can't go. It can carry more sophisticated instruments of larger mass than the Ingenuity helicopter to perform imaging and spectroscopy measurements, to contribute to understanding science themes like geological mapping, other characteristics of the atmosphere, and also being able to make other types of sampling and collection measurements, which could be done in conjunction either with other landed assets on Mars or even with other aerial vehicles. And again, as was the case with the Ingenuity helicopter, which had 72 successful flights, it contributed to the science of the Perseverance mission, because while the Perseverance rover had the ability to drive autonomously and still does wherever it needs to go, it was able to scout out regions to help inform the science team on potential regions of investigation that otherwise would have taken more time and resources to explore. And as you can see here, the helicopter has the ability to potentially fly into caves and to make observations that otherwise would be inaccessible. So it's really a very potentially exciting future science capability that would really open up our understanding of the habitability of Mars. So finally, I do want to touch on the Deep Space Network. So we are actually in the process of developing and building a mission called Veritas, which is going to make measurements with other flight missions of Venus. And Venus actually has a lot of secrets because in some sense it was a lost habitable world. It looks a lot like Earth does in some ways, but as you know, it's an extremely hot environment due to the clouds that actually enshroud the entire planet. But it turns out that we want to make precision gravity measurements to understand the interior properties of Venus, to determine its core size and other properties of its deep interior. So together with the station number 15, the Deep Space Station here in Madrid, we can form an interplanetary instrument by connecting its Ka band transmitter with the radio on Veritas. And that will help us form and create essentially Earth to Venus, well, not an interferometer, but an Earth to Venus gravity measurement. And that will allow us through that large instrument to characterize properties of the deep interior. So we're very excited about the role that the station here in Madrid will contribute to this measurement, which will be a first-of-a-kind measurement. Another way, and in fact I had a chance to visit the station today, it's really quite an outstanding and beautiful place. Another area in which deep space antennas and the DSN will have an important role for science measurements is understanding the properties of magnetars. So within California, we have something called the hybrid antenna. It's a combination of an optical and radio antenna. So you can see the optical device there on the antenna surface. And it will allow us to search for optical counterparts of these magnetars, which are essentially neutron stars. And a neutron star is really just the remnants of an exploded supernova. But we can measure properties of these neutron stars in the radio frequencies, but they also have optical properties which have not been observed. So using a technology which is this hybrid antenna, we hope to find these optical counterparts. So why don't we learn a little bit about what magnetars are?
In April 2020, astronomers detected an unusually bright and powerful radio signal never before recorded in our home galaxy. The source is a magnetar, a type of compact object with the strongest magnetic fields in the cosmos. Like pulsars and neutron stars, magnetars are the crushed cores left behind when a massive star explodes, but their super strong magnetic fields put them in a class by themselves. The fields are up to 1,000 times stronger than typical neutron stars, and over 10 trillion times stronger than a refrigerator magnet. They can rip molecules apart from thousands of miles away, distort the shapes of atoms, and store enormous amounts of energy. On April 27th, the magnetar, named SGR 1935, produced a rapid-fire storm of short, powerful X-ray bursts that lasted hours. The activity, first spotted by Swift, was also monitored by NASA's Fermi Gamma Ray Space Telescope and the NICER X-ray telescope on the International Space Station, along with other space missions. As the storm wound down early on April 28th, NICER recorded some 200 X-ray bursts in just 20 minutes. Later that day, SGR 1935 fired off another X-ray burst. This time, though, it was accompanied by something new, a powerful pulse of radio waves, lasting 1,000th of a second. CHIME, a radio telescope in British Columbia, led by several Canadian universities, discovered the signal and determined it came from the vicinity of SGR 1935. Another experiment, called STARE-2, and operated by Caltech and NASA's Jet Propulsion Laboratory, saw an even brighter signal at different radio wavelengths. Since 2007, astronomers have been trying to understand the sources of powerful millisecond radio signals called fast radio bursts, seen from other galaxies. Magnetars have been prominent suspects. The duration and energy release of SGR 1935's radio signal is closer to fast radio bursts than any other source. For the first time, astronomers saw a magnetar in our own backyard produce a signal only previously seen in other galaxies. The discovery strengthens the case that magnetars are responsible for at least some fast radio bursts. Data from NICER and Fermi on X-ray bursts at the end of the storm showed that they differed from the one that coincided with the radio signal. This event's characteristics set it apart from the other eruptions, and further study may provide clues about how it also powered the radio burst. Radio waves from normal pulsars originate high above their surfaces. Exactly where and how, we don't know. A big eruption could launch a cloud of plasma to high enough that a radio burst could form. Never before have astronomers seen a fast radio burst so close to home. It's just one more reason to watch the skies, and to keep tabs on the strongest magnets in the universe.
Well, it's very much been my pleasure to be with you, and I am very pleased to introduce Kevin Coggins of the Deep Space Network, who will tell us much more about it. So thank you.
Testing. All right, I think we're good. All right, well, good evening, everybody. For the last presentation, muy guay. That was cool. Did anyone see the large spacecraft in the previous briefings, the Europa Clipper or any of those? Did anyone see the big antenna dishes on them? You see those? They're talking to the Deep Space Network here in Robledo. I couldn't be more excited to be here this week to celebrate the 60th anniversary of the Deep Space Network. I want to welcome General Moises Fernandez, the director of the complex in Robledo. Welcome. The amazing science you just saw, we wouldn't be able to observe it, use it, if it wasn't for these large antennas we have to pull that data down to the Earth. It's quite amazing what we do with Spain and our partnership to allow humanity to access all the secrets of the universe. The secrets of our sun, the secrets of our solar system, exoplanets, magnetars, land spacecraft, and worms, right? On other planets. It's absolutely amazing. So tonight I want to talk about our shared journey through the cosmos in context of our communication networks. And I'm going to tell you some things you might not have known. Our partnership with Spain has been going on for some time. In the 60s, after years of collaboration with Spain, including locations like the Canary Islands, we came to an agreement to build a deep space network together, to have the ability to do space together. And we built several sites, one in Canberra, Australia, one in California near JPL, and one in Robledo de Chavela, 54 kilometers west of Madrid. It was chosen because it was near good infrastructure, universities with amazing world-class talent, and it was very free from radio interference, because those are really big antennas. They're like really big ears. You don't want a lot of noise around them because they're trying to listen to these very sensitive signals that are extremely small. Extremely small. We'll talk about that. The Madrid station was the very first to receive images from a planet other than Earth. With the Mariner 4 mission in 1965, images of Mars came in. Then it was the first to receive an image of an outer planet, Jupiter, from Pioneer 10 in 1973. It also supported Apollo 11 And some very important words came through the station. One small step for man, one giant leap for mankind. These pictures, these words, that's the motivation for all the rest of the missions we talked about, because we showed we can go there and we can get data back. We can send a person there and we can hear them. And so, sir, you have an amazing mission. And I appreciate what you do in leading that team. The Deep Space Network site in Robledo is one of 3 with these large 70-meter antennas. If you were to place one of these antennas in a football pitch, you couldn't see the grass. They are enormous. But the one in Robledo is the only one with 6 antennas. And we'll talk about that in a minute. So these are the networks we use around the world to talk to deep space missions. I talked about the 3 DSN sites on the left in California. You can see the one in Madrid and the one down in Australia. We also have sites in Antarctica, in Hawaii, all over the world, and we have satellites in space that provide an Earth relay network. The next place we're going, though, together is the moon with the Artemis missions. And so now we have antennas, more antennas like the one we just signed an agreement with South Africa for, to talk to the spacecraft that are going to land on the moon, to orbit the moon, to fly to the moon. And we also just awarded a contract to a company to put GPS on the moon so that we can navigate on the moon. We're slowly moving out into our solar system. It's quite amazing. But the communications with all these missions will come through the Deep Space Network. So how does it work? We talked about the antenna and the size of it, but how does it really work? It's quite hard, actually. There's a lot of very difficult physics involved. Well, here on Earth, we have to point at the spacecraft, so we have to know where it is. So we're always asking the spacecraft, tell us your telemetry. Which way are you headed? How fast are you going? Where are you? Because we've got to point very precisely at it, because some are so far away. But the spacecraft's job is a little harder. It's got to point at us. And so we've got to make sure we give it a command to point exactly at us. Because if we're off a little bit, you can't hear it. So recently, did anyone heard of Intuitive Machines and the lander they sent to the moon? They sent a lander to the moon, and it was supposed to land a certain way and be able to point directly at us, and use really small antennas on Earth because the moon's not that far. Well, it couldn't because it kind of tipped over, and its antenna was kind of aimed in the wrong direction at the ground on the moon, not back at us. And so I was actually driving in California off the Deep Space Network site, and the driver, a guy named John, his phone rang, and it was the people in Intuitive Machines saying, hey, we use that really big antenna to try to talk to the moon? And so we did. We activated the Deep Space Network, we aimed that antenna at the moon, and the energy from that little spacecraft that landed would hit the moon, bounce off the moon, and come into those big ears. And that's how we got the data back for their mission. And so it was an amazing capability that we were just able to point it at the moon and rescue that mission. 24/7, we can see every spot of the sky because of where we put these big antennas around the Earth. But what you didn't know is that we have this model called follow the sun. When the sun is up in Madrid, the experts that work for Moises are running the entire network. They're controlling the antennas in Australia, they're controlling the antennas in California, and the antennas here. So they're not just operating a third of the network, they're managing the entire Deep Space Network for every mission we have out there. So a few cool things. You guys saw the James Webb Space Telescope? It's one of the many missions supported. You've heard of Voyager. We'll talk about that next. The missions to Mars, the Europa Clipper mission that just launched. Each of those is going to communicate back through this network in Robledo and bring us amazing data back. We may discover life on another planet from the Europa mission or a follow-on mission with an amazing worm from JPL. And that data is going to flow into this valley, not far from here, and then go all over the world to scientists everywhere that are very eager for that discovery. We're here this week celebrating 60 years. We had many representatives of the Spanish government at the site yesterday, representatives from INTA, our partners here in Spain, representatives from the Spanish Space Agency, and representatives from all over NASA, scientists, engineers, people from the Deep Space Network complex in California that run it there. And we were there to celebrate with the workers the amazing things that we've done for 60 years. And we just signed a new agreement to continue our work, and we're looking forward to doing it for another 60 years. This is a capability that will always be part of our backbone for space exploration. Well, let's talk about a historic first. So this picture on the left is one of my favorite pictures. If you look carefully, you'll see 1, 2, 3, 4, 5, 6 antennas all pointing in the same direction. This amazing photo was taken one night by a security guard at the complex. The lighting was just right. It's historic. It's the only site with 6 antennas, but it's the first time 6 antennas have been aimed at the same spacecraft. Can anybody guess what spacecraft it was aimed at? It's on the slide. Voyager 1. So Voyager 1 had some issues, and we're having trouble communicating with it. And normally we just use one antenna to talk to it, right? Because that's all it takes. But Voyager is out of the solar system in interstellar space, past this bubble called the heliopause that's around our entire solar system, caused by the sun. Voyager 1 and 2 punched out, and they're out in the middle of nowhere where no one's ever gone before. And they're telling us valuable things that, weren't even part of their mission profile. They were only supposed to visit a few planets and be done. This mission has been going on for a long time. Well, we had these problems with the software on Voyager, and we think that what happened was some kind of particle was ruining the memory. So we had some bad memory cells or bad transistors. Well, the engineers back at JPL, they've been working 24/7 since the fall to try to figure out what's wrong with the spacecraft. The signal coming back they couldn't understand it. They could record it, but they couldn't make heads or tails of it. They brought in some engineers that were retired, right? And they would look at the codes coming back to see if they could understand it, because they could read the code from all their experience. And they had a young engineer who could write in Python code, write some software to make sense of the signal they were receiving. I remember sitting in the room watching while they were making some discoveries about what was going on. But then I saw in context what made this really hard. When those big antennas send a signal to Voyager, it takes 22.5 hours to get to the spacecraft. And then Voyager does some calculating and sends a signal back. And it takes 22.5 hours to get the signal back. So you say, "How are you, Voyager?" And you go home. You eat dinner, go to sleep. You wake up the next day, you run into work, and you go to the computer, and Voyager goes, "I'm not feeling too well." Uh-oh. What's wrong? And you go home, right? That's what they were doing for months and months. And if the signal was going to come in on a Saturday, they came to work on Saturday. And they were there all day Sunday analyzing the data. And then Monday, they think. And then they waited. Is it going to work? Did I just break it and make it worse? Will I be the engineer that broke Voyager 1? Right? Or will we be the team that fixed it? They were the team that fixed it. And not long after they fixed it, we arrayed these antennas to talk to it. It's quite historic. It's pretty amazing. The antennas have these numbers, right? Antenna 63, which is the big one, and then these smaller ones have different numbers. And you can go to this link at the bottom of the page on an internet browser, you can see the antennas and then the code for the spacecraft they're talking to right now. VGR1 and VGR2 is Voyager 1 and 2. It's pretty amazing. And I'm quite, we've seen that photo reproduced many times because it's one of the most popular ones. How many more years do we have of Voyager? We don't know, right? The batteries could run out. They've already had other kinds of issues, and the engineers that are keeping them alive are just doing amazing things. 22 and a half hours there, 22 and a half hours back. It's incredible. The next giant leap is we're going back to the moon. But we're not just going back to the moon. We're going to have a sustained presence on the moon. We're going back to have habitats on the moon, to have rovers on the moon, to do more science on the moon. But why are we going back to the moon, right? There's many things we're going to learn on the moon that are going to benefit us here. We're going to be able to discover what the moon's made of. We're going to be able to do different science on the moon, even science with medicine, science with plants, science with technologies that will help us. But one of our big goals is we want to prove out the technology we're going to need to do the same thing at Mars. And that's going to be incredible. We call it our Artemis program, but we also in the agency call it Moon to Mars. We're going to go to Moon so that we can go to Mars. That's going to be incredible. The key thing is we're going to do it together. The return to the moon is about partnerships, and this is part of our shared journey to the cosmos. We have the Artemis Accords, where we've got these norms and practices for space and our program for Moon to Mars, and it's growing so fast. I know Estonia just joined, I think Chile just joined, and I don't know who's next, but the number's probably, now it's probably like 46 members, or it's just growing so fast. And as you can see, Spain is a member of the Artemis Accords, and we're proud to be sponsored or partnered with Spain on it. 46 members and counting. But this also means that the technologies that we're developing, we're all developing together. JAXA, the Japanese space agency, is contributing many things: a pressurized rover, some life support capability, and also they're also going to work with us at NASA with a GPS-like system on the moon. And ESA is working with us on that as well as Orion's European Service Module and the Lunar IHAB Lunar View Module that will allow us to see the moon. But ESA is also, through their Moonlight program, developing GPS for the moon. The difference is the satellites from the US, from Intuitive Machines, from ESA, and from JAXA will work as one team. Here on Earth, we have GPS and Galileo, which are different, but on the moon, they will work in one network and one team for the astronauts that we send up. We also have the Canadian Space Agency. We also have many other partners providing many different things for what we're going to do on the moon, because we don't want to do it alone. We want to do it together, just like we do the Deep Space Network here on Earth. This is my second time in how long? 5 months? About 5 months ago I was here. I think I see a few familiar faces as I look out in the crowd. Since I've been here last, we've launched Europa Clipper. We've watched SpaceX land a booster and catch it, right, with tweezers. We've had amazing communications with Voyager spacecraft. We've had a period of heightened solar activity that we understand thanks to many missions, including the Parker Solar Probe. But it's been a very busy year for the Deep Space Network. All that data comes through these antennas. And some of these antennas, if we've been doing this for 60 years, are quite old. And this team works so hard not just to operate them, but to give them really high reliability, to keep them running, because we don't want to lose any of this data. And so again, Moises, thank you for the great job the team does here. And I'd also like to invite Senor Talmo Fernandez up for a nice gift for having NASA speak at the Planetarium. This is a model of one of our Deep Space Network antennas with our logo on the bottom representing each of the three.
Okay, thanks a lot.
Thank you so much.
Thank you very much. It's been a pleasure. You already have another video, okay?
What's that?
You have another video of the Artemis mission?
I do.
Okay. Thank you anyway.
Thank you.
Thank you to all of you. Later on, you will have some questions with them. They will be.
Do we have the video? There we go.
Okay, yeah, you just press the right button. Yeah.
All right. Thank you. All right, thank you so much.
Thanks a lot. Before the question, I must say something because here is the director of the Airbus company, who is a sponsor of the Planetarium as well. And the service model of this Artemis has been done by Airbus company. I just have to say because they pay us, so I have to say.
Yeah, absolutely.
Okay, if you have any questions for all three of them, please come here and they will answer. If you need some translation, I will do for you.
Okay. First of all, here.
Hi.
First of all, thanks for your great job. Not only in representation of the medical people, but in representation of humankind too. What do you think is or was the most challenging mission in turn to launch in the outer space?
The most challenging.
That's a good question.
The most challenging to launch. That's a good question.
Probably the very first one.
Yeah. Yes.
Right?
Yes. Well, maybe we'll each come up with an answer. Well, it was recent, but, I might say it could be Europa Clipper. As we mentioned, it was, or it is, the largest planetary spacecraft that's ever been launched. It's well known there was some challenges that we overcame associated with ensuring that we can get the launch off on time, having to deal with protection of some components that are sensitive to radiation. But we had a very strong team that really within a matter of weeks came together with a solution, got it implemented down at the Cape in the U.S., verified that the approach would be successful and allowed us to meet that deadline. And the spacecraft is very healthy and performing successfully. So there were a number of challenges to be overcome, but we're very excited about the future that will be unveiled. Clipper will make a flyby past Mars and then past Earth for gravity assists, and it should arrive in the Jupiter system in about 5.5 years.
I'm going to add to that and think about, I highlighted both the Curiosity rover And it's very similar to the Perseverance. If you think about that, I mean, you saw how that entire system came together. Those are like 3 different spacecraft that had to be put together and put in the top of a rocket to get it launched. So you have the craft that had to get it there, and then you have the rover itself, and then you had the sky crane, and they had to all be sort of nested together and put together to launch. So the challenges of doing that to create a system that has to work a certain way when it gets to its destination, but you also have to get it off of Earth and define space in a launch vehicle. And it also point to the James Webb Space Telescope. You know, here's this great telescope, and it has to be huge. Now we got to put it in the top of a rocket and get it to its observation location. So many different challenges. I think they're all challenging, and they have different challenges, but we have innovative and creative people and teams of people who face those challenges and create these amazing missions.
So I'm going to add, but just a different view. I think the Apollo missions were the most challenging. We'd never done that before. And not only that, the infrastructure we had to set up around the world to do Apollo is amazing. Antennas all over the world. There were teams that built towns. Towns were built so we could build infrastructure around the world just for Apollo. If you go to the Robledo site, you'll see an antenna from the Apollo era that is still up, that is still standing there right behind the main building. And so the human ingenuity across nations that we had to harness to do Apollo is one big part. But then, for the first time, launching people to the moon, right? After having never done it before. You know, and it was fraught with peril. People died, right? It was very hard, very difficult. We learned a lot of things in that time. And so Apollo is my vote. And we did it. We did it. And we had the words come through the station in Robledo, right, as that proof point that we stepped on the moon. Thank you.
Okay, so first of all, thank you so much for having here, and like everything was amazing. So thank you so much. And then second of all, like kind of following up with his question, like what has been not the hardest or more challenging project that you have worked on, but like the one that you have most enjoyed doing?
Wow.
That's a good one.
That is a good one. So I like the question, Joy, you know, having that part in there, because certainly I find myself saying all the time, I get to do this. You know, I get to do this amazing work, because there's just joy and, you know, such a great satisfaction. I don't say I have to go to work. Like, I get to go to work and to be part of this amazing endeavor. So again, it gets hard to pick one, but ones I was close to, like I think about the mission that I showed you, the picture of me in front of the spacecraft, that was 7 years of my life. And you know, I spent a lot of time away from my children who were little at the time, and to think about the way I felt when we finally got that mission launched, I get chills thinking about it now, the satisfaction I felt to know that this mission was on its way, and the role that I played with this amazing team to get it on its way. And here we are 20 years later, and it's still producing amazing data brought down by the networks that we have at NASA to help us understand better about the atmosphere of our home planet.
That's a great question. I would say for me personally, we did talk a lot about the large strategic missions that NASA does. But I've been fortunate also to be involved in many small satellite missions using satellites that you could hold in your hand or around the size of a refrigerator. And I think what I've enjoyed about them is that they can be very rapid. They often involve a lot of students. In fact, I've worked with high school students that have launched these missions. So I find that it's been very enjoyable, particularly because it's also a way to rapidly increase the rate of our science return and to grow the number and diversity of new principal investigators. You know, you might someday be a principal investigator on a small satellite mission if you choose to. So I think for me, that experience, in particular, working with the students and universities and introducing them to the capabilities that NASA has, including the Deep Space Network, where we have sometimes used DSN capabilities to track some of these missions. It's really been very, very enjoyable.
See, that's a hard question for me because the unique thing about working in space communications and navigation is every mission comes through our network. So we get to work on all of them, right? And it's neat. We get to work on every single one of them because the data comes through our networks. And so I've had a lot of good experience at NASA, really fun times with a lot of different missions. But I gotta say, what we're doing on Artemis is probably what's exciting me the most. It's hard. These are hard problems. We're gonna be putting relays and like a GPS around the moon. That's exciting to me, right? Because GPS here on Earth enables everything. But enabling that Artemis mission to happen, to get humans safely there, set up habitats and get humans safely back from a communications perspective is exciting to me. We will always be monitoring the humans. So the data link always has to work. When you look at it on TV, you're gonna want really nice video. So the data link has to work, right? And so when they need more supplies, we get the data back. Hey, we're out of ice, right? The data link has to work. And so it's exciting to me because we're in that build-up phase. We learned from Artemis 1. We're getting ready for Artemis 2. We're already planning for Artemis 3, 4, and 5. It's exciting. It's very exciting. Thank you. Good question.
Hi. So first of all, thanks for the amazing presentation. My question is regarding alien life or possible alien life. We have no idea how it might be or what it could be made of. Maybe it's carbon-based, silicon-based. And if we eventually find it, we'll have to interact with it as a way to measure how it works or how it is. And that, at least I think that would cause like cross-contamination in some way. Is anyone at NASA actually thinking about methods to take measurements of possible alien life and to not contaminate them?
I can take this one. Yeah. So two things. We have a field of astrobiology, and this is, looking at that question and how do we even detect life elsewhere? We're challenged by even how to, with our instrumentation, detect life as we know it, meaning Earth, stuff we can recognize here at Earth. One of the big questions is how do you detect life as you don't know it? And so that is a big question, and we have a field of professionals who are looking at that. We also have the practice of planetary protection, and in my presentation I showed you one of the choices we made at the end of the Cassini mission to fly it into Saturn, because we were deliberately thinking about not creating a situation where a human-made spacecraft would crash into one of those mini moons, around 146 moons, and that might have biological potential. So we are very deliberate in two-way planetary protection. So how do we protect places that we can go to with our technology and make sure we don't contaminate those areas if they have biological potential? And also, if we bring stuff back to Earth, like we're going to be bringing samples back from Mars, the first time we're going to bring samples back from a planet, how do we make sure that we're protecting Earth from whatever we bring? So this is another very important discipline that we think about very seriously.
Yeah, absolutely. As Andrea mentioned, we do have, the field of planetary protection. That goes all the way back to the Apollo era, in fact, with the science and research that was done with the human missions, and that will continue to go forward. And, we do have scientists that are using their background in organic and inorganic chemistry and other techniques to build and design new types of instruments that would have a broad range of capability to try to assess either the fundamental chemical signatures of life or actual life constituents in the observations that are made, either in situ, if we were to fly through the plumes of Enceladus, or historically through the samples that will be returning from Mars. So, you know, I do very much believe we have the capability to make these measurements and to understand their significance.
Hi. First of all, thanks for coming here, and the presentation, it was amazing. I really admire you. I have like 2 questions. The first one is, how many people typically work on a single mission, such as Europa Clipper?
So we have that about 4,000 team members. I'm looking at, yeah, that's the last I heard, if you count, yeah. So really amazing groups of people. I would go back to the joy question, because one of the joys I think we get is working in these amazing big teams to do this amazing work.
Yeah, and they're diverse teams, and you know that's a real strength in order to achieve mission success. You know, everyone understands their role, and everyone contributes, and you know have a joint feeling of success and accomplishment when these missions launch and make their discoveries.
And I will add that in the science, with I showed you that's 140 missions we have underway at each time, any time. Many, if not most of those missions involve international collaboration. So we use the expertise across the planet. We don't expect to have all of that expertise in the United States, and this really is an international endeavor on behalf of humanity.
Thanks. My second answer is, if you have a maximum time frame to complete a mission.
Yes.
Well, in terms of, there are many phases of mission development which go from the idea stage through the implementation, through its operations, and even the long-term post-data analysis to make discoveries even after the mission has completed its primary objectives. So there are definite, you know, timetables that must be met to meet launch criteria. We talked about the importance of that for the Europa Clipper mission that just occurred. But for those of us that have been on flight missions, you know, some of us feel that you never leave the mission, even if you move on to another job, because you'll never know when you'll be expected to get a call, as was the case, as you mentioned, right. Kevin, with Voyager 1 to help support the mission. So I don't often think about it in terms of a time frame ever really ending, and I think that's part of the joy of it.
So I'm the one who worked at NASA headquarters, and you know, for 10 years, and so that's the part. That's, you know, the business, you know, side that says when we do missions, you have to do it in a certain schedule, and you have to do it within a certain budget and with acceptable risk. And we track that all the time through our phases. So this is a very important part of our work. And I say there is a role, the project manager, and I say the project manager's role is to make the scientists and the engineers uncomfortable, because the scientists are always going to have new ideas about how they can get more and more science, and the project manager's like, you're stopping, right? And we're not going to add the latest detector. We're not going to do that, because we'll never ever finish this project if we try to always do the latest thing. And the engineer is going to want to make it perfect. And the engineer, when they run into problems, they're not going to be able to go back to square one, create their perfect solution, and do a do-over. They have to live with kind of, you know, the less than most eloquent engineering solutions. But that's what actually makes it so beautiful in the end, because you get this amazing science with all these kind of imperfect decisions that you have to make along the way in order to actually get things built within a certain time frame and within a certain budget.
Well, now I'll give you a Deep Space Network perspective. We have a lot of antennas. Well, let's say I have 100 missions today. And some of those missions, like Voyager, maybe they're supposed to end, right? And then I got more missions come in. And so hopefully tomorrow I'm doing 100 missions. No, they did not retire. They did not end. So today I'm doing more than 100 missions. And so my team was like really good at scheduling 100 missions. So we're like, hey, now, by the way, we know you planned this week to only do 100, but there's 150 because these missions aren't ending because the science data they're getting is still good. And so the number is not actually 100, but the point is that with the Deep Space Network, right, we're running a communications network here. And I only thought I'd have this many customers this week, but because some of these missions don't end, we have to figure out how to do this thing called scheduling. And what we find out is sometimes we may not have enough capacity, and so we may have to build a 6th antenna in Robledo, right? Or another antenna in South Africa. And so for us, you know, as these missions don't end, we actually have to change to have more capacity. And so that's just how we feel in the Deep Space Network, right?
So I'm going to add something just to give shed a little light on these what we call extended missions. So I've mentioned a couple of times that I was working on this mission that launched 20 years ago, still operating and doing great.
Yeah.
We designed it for a 5-year mission, and that's most of our missions are, you know, sort of in that time range, right? But we overperform, and we make these amazing missions, and often their discoveries happen when they're in their extended life. But we have a process in science called a senior review, and we get our greatest minds in each of these science disciplines, and we have them look at our missions, take a look at what data are we getting, what discoveries, what's the health of the spacecraft. We have to consider, you know, the communications, maybe not as much as you would like us to do, but we make decisions about having them continue because of the scientific value as seen by the scientific community. So that's a part of this process. They don't just go because, hey, there's still got gas in the tank and we're gonna let them keep going. But there is a very deliberate process looking at its scientific value before we make those decisions to extend them.
So in summary, yes, there's a timeline, but if there's more goodness to be had, we want that too.
Good evening. Thank you very much for all of this. And I'm really interested about how the Perseverance, the robot, and also the Ingenuity, the helicopters, communicate between them, and also if it would be possible to connect more devices like sensors or something like that, like IoT technology. I don't know. Thank you very much.
So it sounds like the question is, how does Perseverance and Ingenuity and Perseverance communicate? And I'll ask Kevin to correct me. I think Ingenuity has a UHF radio that it communicates with the base station on the Perseverance rover up to Mars orbiting assets like the Mars Reconnaissance Orbiter. Right. I'm not sure if Perseverance talks to Odyssey as well. Probably I should ask Leslie. Yeah, Mars Odyssey. So there is a bent pipe relay through which that's what we call it, through which the Ingenuity helicopter was communicating through the rover with orbital assets back to Earth. And it's the same path that Perseverance uses to communicate back to Earth as well.
So we've learned a lot from how Mars does this relay type capability and communicates back to Earth. When we go to the moon with Artemis, we're going to have all kinds of robotic science missions. We're going to have habitats, rovers, astronauts walking around, and not all of, they can't all talk right back to the antennas on the Earth. So we're going to have base stations on the moon that aggregate, and we're actually going to use Earth-based technology in many of those, like the same way our cell networks work here on the Earth. And then we'll move up to some big relays in space around the moon, relay satellites, as well as some direct-to-Earth links from the surface of the moon to get all the data back to the Earth. So it will start to resemble and use IoT technology. It's a very good question.
Hi, good afternoon. Thank you very much, Mrs. Razzaghi, Mr. Norton, and Mr. Coggins for your presentation tonight, and for sharing all the incredible things that NASA does here in Spain. My question is just curious about the incredible images that we got from the universe. So it has now seen the presentation. Wonder me, how do you manage to count and recognize what you see in the images?
I guess that you might have like math models that help you to do that. But I'm curious about to know the criteria that you use to explore those images and recognize which ones are exoplanets or stars or other planets. And my last question is, this is an idea that I've got, but maybe you can correct me, and is that the images that we got are outdated because of the time that light takes until the device that are taking them, and then from that device to the antennas. So if that approach is correct, maybe do you have an estimation on how outdated are those images that we are seeing in our browsers online? Thank you so much.
It's a great question. Shall I start? I mean, so we saw some wonderful images from the James Webb Space Telescope. We've seen some other images. That's not exactly what you see from the perspective of the instrument. Most of the imagery that we see is processed once the data is transferred to the Deep Space Network to produce those visible images that we see. Many of the missions that we fly image the universe in a variety of wavelengths across the electromagnetic spectrum. The infrared is very popular because it provides heat signatures and provides a lot of data and allows us to see through gas and dust that we may not be able to see visibly. So they're really a combination of techniques, and the scientists understand very well what they're looking for and how to analyze that data. There are a lot of modeling tools and analysis tools that they use to derive information from that. So, you know, while many of us may think, and this still happens from the ground, you could make optical imagery from various ground-based telescopes or other ground-based instruments. I would say the vast majority of the imaging that has been done in recent years is based on collecting data and performing advanced processing on it.
I'll just add another perspective. Nothing can travel faster than the speed of light, right? Our radio waves travel at the speed of light. That's why it takes 22.5 hours to reach Voyager. If I were to try to take a picture of Voyager, the light I receive on my camera is 22.5 hours old, because that's how long it took the light to get. With James Webb and with Hubble and in the future Roman, the images they're going to see could be billions of years old, billions of light years away. And it means it took a very long time to get here. But that's all we can see, because that's, if we're looking at these different, optical spectrums, they have to get to us, and so they take all that time to travel. And so there's even a quandary between here and communicating with the moon once we send humans, because time on the moon is even different than time on the Earth. It moves at a different rate because gravity is less. And so in everything we do, we have to account for, these changes in the flow of time and the distance and how long it takes light to travel.
And I would just add one thing. When you think about telescopes, telescopes are time machines. You are actually looking back at the past and seeing something that happened often billions of years ago. Even when you look at the moon, it's a little bit outdated by the time it reaches your eyes.
Hello, happy 60th anniversary, and I have a question about space mining. It's not really a popular topic right now, but does NASA view it as a potential source of funding in the future? And are the challenges that you have to overcome to reach it worth the actual outcomes?
Yeah, I'm not familiar with any specific work that NASA is doing with respect to, you may be referring to asteroid mining, for example, because there are a number of commercial companies that are looking at that as a potential, revenue source, and actually a way also to develop and advance new types of technologies. I think for work associated with the Artemis and the lunar program, we're definitely interested in capabilities that will allow us to access and make use of the regolith on the moon. And there are many commercial companies that NASA is partnering with to explore that. So it is an important topic.
Hi. So thank you for the presentation, and thank you for sharing your experience with us. My question might be a naive one, but I'm really curious, and I always think about that when I watch the news. The thing is that you were talking about the Apollo mission and the Artemis mission or Artemisa mission. And my question is, technology has really improved a lot in the last 50 years. Like, the world has nothing to do regarding technology such as medicine, artificial intelligence, and so on. I could go on. But it sounds like it's still pretty hard to get to the moon. So what are the challenges? Is it about funding, or is it about political priorities, or are there still technical challenges that we still have to address? I mean, because you've already been there. You already have the knowledge, but it still sounds challenging. So well, what is it?
The base challenge is, the first one is gravity. We have to push against gravity and take a lot of stuff up, right? And that's hard. And the second one is, wherever we send humans, we want to make sure they're absolutely safe, right? And so we all need air, we need food, we need facilities, we need and we need to communicate. And so we want to come up with technologies and test them, right? And make sure they are really highly reliable and can survive launch, can survive where we're going to put them in the environment and be safe to operate. And we want to do science while we're there. So we actually have to design science missions and science instruments and other things. And all of these things have never been done before in the ways we're doing them, right? We've learned from things we've done, but it's just the fundamentals of what makes space hard, right? We don't do it every day like we do Earth, right? We don't do the moon every day. And so it's just making sure that we're doing a really thorough, good job so that we plan, and that's why we have so many Artemis launches, right? First one, we demonstrate some technology. The second one, we're going to demonstrate a lot of technology. The third one will demonstrate more technology, and we start doing things in those missions as well. Because at NASA, when we plan these robotic missions, these space missions, these human missions, safety is a big priority, right? But we put a lot in making sure we can actually accomplish our goals.
I think a big difference between Apollo and Artemis is that we're going to stay instead of going to visit. That's a big difference, and it requires a lot more.
That's right.
To plan for being pioneers on the moon as opposed to visitors.
Yep, great question. Thank you.
Yeah, that's it.
Hi, good afternoon. Thank you again for your speech. I am curious about, SpaceX has landed one of their spacecrafts in the initial point where it was launched. So will NASA try to implement this technique with the aim of reusing the spacecraft to reduce the impact in the environment and also the cost of making the explorations?
So I will start with saying that the innovation that SpaceX has brought to the table and our work has been amazing. And key to that is this reusability of hardware. That was a game changer, and that's what made our access to space even less expensive than what we were doing before. Like when I was managing, budgets, and I was thinking about how much it would cost just for the launch, it was a huge part of our budget. And because of this innovation of reusability of the hardware, it has been a game changer, and it has certainly had a very positive impact on our budgets and our ability to do a lot of missions in a more affordable way.
So at NASA, we work with a lot of commercial space companies, and we help them become better. SpaceX is one of those companies. They're actually part of the Artemis program. And these technologies they've demonstrated, catching the booster, are key for the things they're going to do for us in Artemis. So we're absolutely working with them, and we're going to use that technology.
What do you need to do to like become an astronaut?
Well, you need to have better vision than I do.
I would add you have to be really brave. You know, I mean, it's such a brave thing to do, to put yourself on the top of a rocket, and you know, the training that the astronauts go through to be able to do this work is really rigorous, and you have to be very mentally tough to take on these challenges as well. I mean, it's quite an audacious endeavor, and I know quite a few astronauts, and you will notice that I've never been to space. I'm not sure if I have, you know, all of those attributes to do what it takes to, you know, to be an astronaut.
Hey, it's good to see you guys again. Welcome. Great question. So, you know, we get to work with a lot of astronauts, and you know, one thing, and I know your mom and dad want to hear this: make good grades, right? Do well in school. Study hard, right? Study hard. Put yourself in good physical shape, right? Because it's hard. It's hard stuff. But set your mind to it. Decide that's what you want to do. And then, you know, wake up every day, every week, figure out, how do I move closer to my goal today? What do I want to learn? Do I want to talk to an astronaut? How do I do that? I ask people that know astronauts who might be able to help me talk to an astronaut, right? So I can learn more. But set a goal, know your goal, keep moving toward that goal. You can do it.
Yeah, absolutely. And all kidding aside about the vision, you know, I actually do have a friend who's an astronaut, and he's often asked this question. And one of the things he said, I think, is very pertinent. Just be open to a variety of experiences, and, you know, always challenge yourself in new directions. So my friend, he's flown a number of missions on the space shuttle. But he was also asked, well, are you willing to go over to Russia for a couple of years and fly on the Soyuz? And, you know, not everybody jumped at that opportunity, but he did. And, you know, he found it extremely valuable to be there, to take on the challenge of learning Russian, to work in a new environment. And so he's spent, you know, many, many hundreds of hours on the International Space Station as a result of that. So his general message is, you know, just don't be afraid to take on new challenges, and always be willing to extend yourself. He said that's something that those that are reviewing applications look for.
Can I say something about that? The most important thing is also, don't forget to send the application.
Hi. My question was, like, do you think one of your spacecrafts is ever going to reach one point in space where it's too far to communicate, like too far to like do something?
That's a good question. Well, do you see, you know, when we're worried about talking to Voyager, we have to aim 6 antennas at it. I don't have 7 at your site. And those things are moving fast, and they're moving away. So yeah, it's possible. If their power gets a little lower and they send a little less energy, I might not hear it. But you know, that's why we build big antennas. That's why we have so many. But it goes back to the question about extending missions. We extend a mission and it's gone further than I planned to communicate with it. Well, you know, I can't communicate with it. So it hasn't happened yet, right? But it's a great question. Yeah. We worry about that.
Hi, and thanks for this conference. I'm interested in knowing if there are any planned successors to the International Space Station.
Yeah, absolutely. So, you know, the ISS is going strong right now. We have crew missions continuing to go up, to take crew up, to bring crew back, to bring, you know, supplies up and back. But we have this program called Commercial LEO Destinations, where, you know, I mentioned earlier how we work with a lot of commercial companies like SpaceX and others to develop technology and to develop commercial space partners. Well, Commercial LEO Destinations, we have companies that are, I mean, it's amazing. I was just in Milan at the International Astronautical Conference, and these companies that are part of this CLD program are making inflatable habitats to go around the Earth. That when they inflate, there's already structures in them that straighten out and lock in, and they're huge. So look up inflatable space habitat on Google, look up commercial LEO destinations. LEO's low Earth orbit, and there's a whole commercial market booming to do space work. Now, why is commercial doing this now, right? Why didn't they do it before? Well, NASA had to prove out the value of it. The fact, A, we could do it, but we created so much value in the International Space Station in pharmaceuticals, material science, all kinds of things that benefit us here on Earth. Well, now the technology's gotten easy enough with companies like SpaceX showing how much they can launch at affordable prices, that now these other companies are like, I can have a business case. I can actually make money doing things in low Earth orbit. That's usually the way of technology on Earth. Telecommunications started with places like NASA who needed to move data around. Well, we're going to move around these fiber optic cables. Well, I could do phone calls on fiber optic cables. And all of a sudden there's phone companies. And so it's just a natural progression. And now what do we do at NASA? Once commercial starts to come into low Earth orbit, we're going to the moon.
When you're tired, you tell me.
Thank you. First, thank you for sharing all this data with us. So you first, there was a question about Artemis and going to the moon and staying there. The moon is a relatively safe environment and is relatively close to the Earth. But do you see realistic for any human to reach Mars, let's say in the next 50 years, something like that? Because it's like 200, 300 days of travel, right? And then they have to survive two cosmic rays and stuff like that. So I think that's a much harder endeavor there. Do you see like there will be like a distance where humans could reach in the solar system in the next 50, 100 years from here?
Yeah, it's a very deep question. I think, if I were to, give my personal opinion, we need those challenges. And I think that we have the capability to overcome them. So, yes, I mean, I know there are people that are interested in going to Mars if the possibility existed. Do we have the technology and the capability to do it safely and reliably today? Not yet, but we need to have that goal, and I think we need to continue to push toward it. And I'm very optimistic in the sense that with the right amount of focus, effort, and discipline, we can overcome those challenges and make that a reality someday.
I work with radio waves and with communications. And 100 years ago, 150 years ago, they had these concepts of something called the ether, right? Because they didn't understand how things worked. And it would be impossible. They'd say it's impossible for me to be somewhere else, not within sight of hearing, and to talk to someone, right? If you were to go back 100 years and show them an iPhone and do a FaceTime call 100 years ago, they'd lock you up. They'd think you were an alien. They would not understand how you did it. Humans, we have this amazing way of adopting technology, of optimizing it, making it more affordable, catching rocket boosters and reducing the cost to launch mass into orbit tremendously. Everyone thought it would be impossible. Then they saw it happen and we're like, okay, now it's possible. Everyone thought the telephone was impossible. They saw it happen. Well, now it's possible. What do we add to it? Videos over distance? You're crazy. We do videos over distance now. Send spacecraft outside of the solar system. You're out of your mind. We have two. What seems to be impossible today, we as humans, we're really good at moving toward making it possible. And not only possible, but it becomes the foundation for what we build on next. And then that becomes the foundation on what we build on next. And so I absolutely think we'll be on Mars. I think there could be a group in this room in 50 years having a video call with people on Mars talking back, although there will be a time delay.
So we have an expression at NASA, we turn science fiction into science fact.
Well, our speakers should be very tired. So our last question will be from a kid. Okay?
Thank you really much for the speech. I loved it so much. And I would like to ask a more personal question. What careers are required to enter to work in NASA without being American?
That's a wonderful question. That's a wonderful question. I can answer some, you can answer some.
Yeah, well, I will go back to one thing I brought out earlier is that like so many of our missions are international endeavors. We work in partnership with countries around the world. So you can actually be a part of a NASA mission from another country. Indeed, we have many partners who are on NASA missions that way.
So you could be an astronaut with NASA, right? We have many astronauts that aren't Americans also, right? Because we have international partnerships. We partner. We do this together, right, with other countries. You can work in the Deep Space Network, right? You can be a scientist at NASA, right? You can design science missions. There is nothing off limits.
That's absolutely right. I mean, you don't even have to be a scientist or an engineer. If you have an interest in business or finance or even construction, you know, there are really many, many careers. I think, you know, space in general as an endeavor is one that's been able to sort of homogenize a lot of our knowledge, you know, for a common goal. And it really does require a lot of expertise. We were talking earlier about the Apollo missions. When the first spacesuits were being designed, there were many technical and engineering companies that proposed building them. It ended up that there was a seamstress company that was the one that actually designed the first spacesuits because they had that expertise. So there's really no limit to the amount or variety of careers that can contribute to exploration.
Have you strength for one more question? Or
Absolutely, yes.
There is a kid also here. Luis. Priority the kid.
I think everything was awesome. And I have some questions, okay? And the first one is, after seeing Apollo and Artemis, why do they put the names of the Greek gods?
Oh, that's a very good question.
Great question.
So I was probably younger than you when the decision was made about Apollo. But I know about the decision for Artemis because Artemis is the twin sister of Apollo. Yeah, and one of the main goals is to actually have women be a part of the next moon mission. So I can speak to that. But I'm not sure about the original Apollo name, to be honest.
Yeah, I can't recall.
Help from a NASA friend.
We call a friend.
Oh, wait. Greg knows. Come up, Greg.
They were brothers.
Greg doesn't know, but I would speculate that these are from the myths, from those that came before us, and those myths are bigger than all of us in our dreams. And I think that's where they came from. We look back to people who dreamed big and first looked up at the sky, and a lot of those Greek myths and Greek gods represented in the heavens and the stars, and I think that's where that came from. Andrea is right that we purposely chose Artemis to pair with Apollo, but I think that's where the Apollo program chose from.
If you are interested in that, we have an exhibition downstairs about that.
And, you know, I just can't resist in terms of the naming and with respect to the Deep Space Network. So there's a very important radio that was developed at JPL called the Electra radio. But I talked about small missions earlier. there's another radio called the Iris radio, and I believe Iris was the daughter of, I'm going to forget, but there is a relation between Electra and Iris. So I think it's very common to try to find these types of themes in naming of both instruments and missions.
And I'll add that our Mars, like the Curiosity, Perseverance, the Sojourner, Spirit and Opportunity, Ingenuity, these were all from contests for students, from young students that participated in a contest to name those missions. So yeah, that's one way we've engaged students in our mission.
And now the last question. There, down there.
Hello, I had a question. What was the most relevant or important thing that we discovered when we exit the solar system in the Voyager mission?
I think actually detecting, as Kevin mentioned, where the heliopause is. You know, there was a lot of modeling that was done and theory based on something called magnetohydrodynamics modeling to try to estimate sort of the size and the location and the position of the heliopause, which is that boundary between the influence of our sun and interstellar space. But when Voyager actually was able to conclusively discover that we've crossed it, that was a very significant event because it was the first time a human-made object has actually traveled beyond the bounds of our solar influence. So that was really, really very significant.
All right. Well, hey, thank you so much for coming out tonight and for these amazing questions.
Thank you.
They were great questions.
I have another last question. Have you enjoyed your stay in the Planetarium?
Absolutely.
So
Absolutely.
much.
Yes,
Thank you so
Thank
much
you very
for
much.
having us. It's been a
Thanks a lot.
pleasure.
Thank you.
Welcome here.
Thank you so
Whenever you
much.
like. So thanks.